Yeah, it works. Yeah. Shall we start or?
Yes, so before starting, so I would like to remind you to sign the sheet if you didn't do it. Then that said, I think we can continue with the second lecture by Jérôme Dubail.
Third.
Third.
Yeah.
Sorry.
Yeah, okay, thanks, Vincenzo. All right, so just a quick recap of what we did on Friday. So, okay, so on Friday I introduced a model, which is the free boson conformal field theory, nowadays known as Gaussian free field, which is the simplest possible conformal field theory. And the reason why I did that, the reason why I wanted to focus so much on this specific model is because first of all, it's by far the most important one in terms of applications to statistical physics and condensed matter physics. I'll try to give you some I'll try to explain this in the next lecture. But second, as we will see later today, the general discussion of conformal field theory is sometimes a little bit abstract, and so it's always good to have one concrete model where you know how it's defined and you know how to calculate everything, so that you can always turn to that model to see how the general ideas work in that particular case. So that was the motivation for talking about this specific model. So remember that it is defined as follows. So we saw that Gaussian probability distributions are always defined by the two-point function, and then you just use Wick's theorem to compute anything, to compute any higher order correlation function in the model. Now the Gaussian free field in particular is defined is in an infinite dimensional distribution defined as follows. So you take the two-point function to be the Green's function of the Laplacian. So some of you asked me what happens if you replace the Laplacian by a Laplacian plus a mass. So instead of looking at minus the Laplacian, you take minus the Laplacian plus a mass squared. So that would be the Klein-Gordon operator. So what happens in that case? I mean, you can also play that game, but in that case, you will get a massive boson. Okay, so the general discussion works in the same way. So that's fine. The big difference is that now you introduce a length scale in the system, which is 1 over the mass, and so this doesn't nicely at all under conformal transformations. So that's the reason for taking the mass equal to 0. It's that we want this to describe critical systems that do not have a specific length scale, and because we have taken this mass to 0, things behave very nicely. Emphasized quite a lot the role of short distance regularization. This is a key point because, as we will see today, if we do not pay attention to short distance regularization, then we are missing the main points of the theory. And at the very end, we arrived at the Gaussian free field in a planar domain with Dirichlet boundary conditions. We saw that we could define it from the Green's function, and the Green's function itself we can define if we have a map from this planar domain U to the upper half plane. So if we have a conformal map Z to W of Z that maps to the upper half plane, we saw that this always exists thanks to Riemann's mapping theorem, then you can consider the Gaussian free field in that domain. and this is what the Green's function looks like for a Dirichlet boundary condition. Now I forgot to give you, so I gave you last time 2 exercises about correlation functions of these potentials that are also called vertex. Let me just give you a third one, and then the last one about these correlation functions. So from the definition, you can relate the correlation function of these operators in this domain, in this general planar domain U, to the same correlation function in the upper half. This is H. And the way the 2 correlation functions are related are, so one is equal to the other up to some Jacobian factors. And these Jacobian factors are really the key point, where here delta is, that's called the conformal dimension. So in that case, we have this delta is equal to this delta bar, and it's equal to alpha squared, alpha I squared over 2. So from the definition, you can derive this, and the main conclusion that we want to draw from this is that correlation functions behave nicely under transformations, namely they transform covariantly under conformal maps. And again, this is really coming from the fact that we have a theory without a length scale, without our particular length scale, and this is what would change if we were looking instead at a massive boson. So this covariantly means it's not completely invariant. So if it were really invariant, then this factor would not be here. But if this factor were not here, then there wouldn't be much to say about this theory. And because these factors are there, the transformation is slightly non-trivial, but still it is easy, and we can control what is happening. Good, everything clear up to here? Okay, so now we move on. I would like to spend a little bit more time just on this point splitting regularization, because again, this is a key point, and then we'll move on to the general formalism of conformal field theory. So the point I want to make, and that was section 3.3 in my notes. By the way, the notes are available on the website of the school now, at least for the first 2 lectures, and I think Filippo should put the third one soon. So the key point is that conformal transformations and regularization, so short distance regularization, these do not commute. They do not commute, and so one has to be careful. So recall our definition of point splitting. So we define point splitting as follows. So, and now I'm going to use these chiral components just because it will make the formulas lighter. Okay, so remember that we had defined H. We said that H we could decompose into a chiral and an anti-chiral component, and this is because when it's inserted inside correlation functions, this becomes a harmonic function. Okay, so formally we can do this, And so then with our definition of point splitting, this was the limit when epsilon goes to 0 of phi z plus epsilon phi z, and we subtract the logarithmic divergence, which in this case is just log epsilon. Okay? So now here's the important point. So if we now look at a conformal map from, say, this domain U to the upper half plane. Actually, here it doesn't matter that it's it is the upper half plane. I could choose any other domain, but let's take the upper half plane. And let's say I want to look at this operator phi squared. So I do this point splitting regularization. So I split it. So I put one operator, say here, phi of z, and one operator at a different position, z plus epsilon. Okay, so this is z plus epsilon. And this logarithm here, so I have to subtract this logarithm of the distance between the 2 points, right? So the distance between the 2 points here is this epsilon. But now under this map, z is going to come here, say. This is going to be phi of w of z. And the other point is going to end up here, say. This is going to be phi of w of z plus epsilon. But now if we do our point splitting regularization on this side, then we are going to have to subtract the distance between those 2 points. And the distance between those 2 points is going to be mod of w z plus epsilon minus w of z. And this is, of course, not equal to epsilon, right? Because there is a Jacobian. We pick up, if we do that, we pick up a Jacobian, the Jacobian of this transformation. Okay, so if we do this, if we write the formula that corresponds to this, then we see that phi squared of z. So the point is that there's a different, the regularization depends on the domain on which we are working. So if we regularize, if we do this point splitting we regularize on this side, on the upper half plane, then with the definition of point splitting, this we would write that this is limit of phi w plus w of z plus eta times phi of w of z plus log eta. And this is, as I said, so this is not equal to the regularization in U. And the difference so this would be the regularization in the domain U, but you see that you pick up an additional term, which is the log of eta plus over epsilon. And so this would be phi squared regularized in the domain U plus log of the Jacobian of this transformation. Is that clear? It's simple, but it's an absolutely crucial point. Okay, so now more generally, you can check that phi to the n, if I just want to write this formula more generally, phi to the n of w regularized in the domain U, you can check that this is, regularized in the domain in the upper half plane. This is equal to, okay, some expression that involves some combinatorial factors. I mean, it's not important. I'm just giving it for completeness, in case you want to, in case you want to check it for yourself. You can check that it is this times the logarithm of the Jacobian to the p and times phi of z to the n minus 2p, and now this is regularized in the domain U. Okay, so that's a general formula for this. And now comes a much more important formula. So this implies that e to the I alpha phi of w regularized in the upper half plane. This is e to the I alpha phi of z regularized in U times the Jacobian to the minus alpha squared over 2, and so this alpha squared over 2 we call delta, as I said, as a same notation as here. Okay, so I mean, you see, this is the point is that this is true at the level of the operators themselves. So the operators themselves, if you properly take care of the regularization, they transform in this covariant way. And then if you know that for all the operators, of course, it implies that correlation functions work in the same way. Okay, so that's an important formula. All right, so this means that these particular operators transform covariantly, but this is not true, of course, of all operators. But of course, let me stress, this is, of course, so careful, this is not true for all operators. Right, so in particular, it's obvious, it's clear that if I take one of these operators that transform nicely, and for instance, I start taking derivatives, then it's not going to transform this way, because the derivative is going to act on this term and on this term, and then it's going to generate a sum of terms, and it's going to look much more messy. I mean, we also see here, of course, that just this particular operator here, phi to the n, also doesn't transform particularly nicely. So this is actually the reason for looking at these exponentials here, because these exponentials, they do transform nicely, while most other operators in the theory don't. I mean, you get stuff like this. And now let me just yes. Yes. Okay, and so then let me just. So I think it's clear, right? It's clear that this is not true for all operators. Now there's one operator, one particular operator that's going to play a key role in the theory, and so let me just spend 10 minutes on the transformation law of that one. We'll see later why it is important. So another example of an operator that does not transform nicely. of an operator that does not transform nicely, or not as nicely as those, or say transforms less nicely, but yet important. So this is this operator here, and I'll tell you later why it's important. It's the derivative of phi squared, normal ordered. So let's look at how this object transforms. Let's assume that it's interesting, and let's look at how this object transforms. So, okay, so we use, again, point splitting regularization, but now we need to be a little bit careful because there is this derivative. So the way we can think of it is of taking not 2 points, but 4 points. 4 points, let's call these 4 points z plus epsilon 1, z plus epsilon 2, z plus epsilon 3, and z plus epsilon 4. And we are going to use epsilon 1 and epsilon 2 to generate the first derivative, and epsilon 3 and epsilon 4 to generate the second derivative. So this is going to be the limit when epsilon 1, 2, 3, and 4 all go to 0 of phi z plus epsilon 1, phi z plus epsilon 2, divided by epsilon 1 minus epsilon 2. Then we take, sorry, this is a minus phi of z plus epsilon 2. Here we take phi of z plus epsilon 3 minus phi of z plus epsilon 4, divided by epsilon 3 minus epsilon 4. And then we subtract all the divergences. So let's look at the divergences that we can have. So of course there is a denominator, epsilon 1 minus epsilon 2, epsilon 3, epsilon 4. And then there's a first term, there's a first logarithm that comes from the divergence when this point here comes close to this point. So this is going to be log of epsilon 1 minus epsilon 3. Then there's a second term that is going to come from the divergence of this one with this one. So that's going to give us a factor epsilon 2 minus epsilon 4. Then there's another term that's going to come from this one and this one. This is going to give us epsilon 1 minus epsilon 4. And finally, the last term gives us epsilon 2 minus epsilon 3. Okay? Now, does this thing here, does it ring a bell? Does anyone recognize this? Yes, so this is indeed the cross ratio. So it's the cross ratio that we can cook up out of these 4 points that are all near the point z. Okay? And so as a result, so using the same logic as the calculation we did here, you can see, I'm not going to do this in detail, but it should be clear from here. You can show that so the derivative of the derivative of phi regularized in the upper half plane. So after we have done the conformal map, this is equal to dw over dz to the minus 2 times the derivative of phi of z squared regularized in the domain U plus a term that's coming from here. And what is this term? Okay, I'm going to write it. Okay, it's going to take a little bit of space. Let me write it here. This is epsilon 1 minus epsilon 2, epsilon 3 minus epsilon 4. And then here we pick up the log of the ratio of two cross ratios. So one is the cross ratio after we have applied the conformal map to the upper half plane. Okay, so there are 4 points here. So it's W of z plus epsilon 1, W of z plus epsilon 2, W of z plus epsilon 3, W of z plus epsilon 4, divided by eta of z plus epsilon 1, z plus epsilon 2, z plus epsilon 3, and same thing for the fourth point. Sorry, this is a parenthesis and this is a bracket. Is it clear? Yes. Sorry? Yeah, there's still a limit. Yes, thank you. Yeah, this plus the limit when all these epsilons go to 0. Epsilon j goes to 0. Okay. And this we saw in the first lecture what this was. So we had called this like distortion or conformal distortion or whatever. So it's something that vanishes for special or global conformal transformations, but does not vanish for other transformations. So it has a name. What's the name? Yes, was the Schwarzschild derivative. Okay, so the conclusion from all of this is that if we define, and we will soon define an object that's called T so if we define a certain operator T of z as minus 1/2 times this derivative squared, regularized, then this object transforms in the following way under a conformal map. Okay, so one way to write the formula for the transformation is to say that this T of z is the Jacobian of the transformation squared times T of w, and then you pick up plus 1/12 times the Schwarzschild derivative. This factor 1/12 is just coming from that's the normalization of this Schwarzschild derivative. Remember that the Schwarzschild derivative was defined as w to the 3. I mean, you can compute it. You can compute it from this definition here, from taking the difference of the two cross ratios in the limit where the points coincide, and you will see that this is w3 over w prime minus 3/2 w second over w prime squared. So this here. Okay, so we will basically spend the rest of this lecture on this formula. So T will be the stress tensor. That's the transformation of the stress tensor, and this is one of the most important formulas in conformal field theory. That has many applications. Okay, so that was the end of what I wanted to say about the Gaussian free field, and so now let's move on to the general framework. Any questions? No? Good. All right. So okay. So now we are going to have a glimpse of general 2D CFT. And for today, we are going to focus on the stress tensor and what is called the central charge. Stress tensor and the central charge. Okay, so first, a little bit of general discussion of what we have in mind and of the motivation. So when we think of a field theory, what we have in mind is typically a situation like this. So we have two spaces, or if you want, yeah, like one is a surface and the other one we don't know. So we have a space that's our real space. It's the space on which our theory lives. And then there's another space which is called sometimes target space. That can be anything. Let's I mean, it could be a sphere, could be a line, it can be anything. So we have a surface on which our theory lives, and then there are fields. So we have some points x, and at each point x we have some fields. Let's call them generically psi of x. This could be some vector in some target space, like a vector on a sphere or something. If we are talking about a sigma model or whatever, and then we have a local action, which means that we have a functional. For any field configuration, we have some functional that allows us to give a certain weight to the configuration that takes the form of some local function of the field psi and possibly of derivatives of psi, of something like this. Right, so for the Gaussian free field, this psi would be what we were calling H, right? We would have H would be the field. It will live, H is simply a real variable, so the target space would just be a line, one-dimensional line, and then the local action for the Gaussian free field. Remember, we said we could write it as 1/8 pi integral of gradient of H squared d to x, right? This is our action S. Now, what might be confusing if you open a textbook on conformal field theory is that in practice you never actually work with this. You never worked with the action. Because what you do instead is that you almost immediately integrate out the degrees of freedom. And what I mean by that is, so if you integrate out, by integrating out the degrees of freedom, so the degrees of freedom psi, so the field psi, what you get is a partition function, and the partition function now is just some number that you can associate to a certain surface. So you have this surface, you have the fields that live on it. Then you integrate out the degrees of freedom with that local action, and you get an object that's the partition function. Okay, so formally you may say that you might define this as the path integral of exponential minus f psi. Okay? But in practice, in conformal field theory, one actually never explicitly computes these path integrals. Instead, what one does is that one works with a set of consistency rules that allow to somehow get those partition functions from other types of arguments without ever explicitly computing path integrals. Okay, so just let me just mention that it's also possible in the general framework of conformal field theory to consider domains with surfaces with boundaries. Surfaces with boundaries. So you might also look at partition functions like of surfaces like this, for instance. So this would be a surface with a hole and with a boundary, with a certain boundary here, with some boundary condition, on this boundary here. There's another boundary inside. You could have another boundary condition here. Boundary condition 1, boundary condition 2. I mean, if you think again about the Gaussian free field, you could think of taking Dirichlet boundary condition here and Neumann boundary condition here, or Dirichlet and Dirichlet, or something else. Anyway, so this partition function then would depend, it would be a number associated to the surface itself and on the choice of boundary condition. And on the boundary conditions. Okay, and then so partition functions are the key objects, the central quantities that that one is dealing with when one does conformal field theory, and then the other central quantity are correlation functions. But correlation functions one can always view as limits of ratios of partition functions. So in the end, if you know how to handle partition functions, in principle, you know how to do everything. The reason is the following. So let's imagine I have some surface. Again, let me draw the same surface to avoid confusion. Let's say I have some surface like this, and I have some points, and at these points, I insert some operators. Let's say phi 1, phi 2, phi 3, whatever. Okay. So this correlation function, so the correlation function, yeah, I can always look at, I can always view this as the limit, as a limit of a surface with, say, boundaries. You see, where a surface like this, where I cut a little disk here, and I choose some boundary condition, say boundary condition 1, here boundary condition 2, and so on, and here boundary condition 3. And then if I take the ratio of this partition function divided by the partition function of the same surface, but without these insertions of small punctures, then this would be what I would call a correlation function. Okay, so this would be in the limit where the disks go to points. Anyway, this is just to say that partition functions and correlation functions are not independent objects. On the contrary, they are intimately related, because correlation functions are always ratios of partition functions. So this is what we would call correlation functions of these three operators, phi 1, phi 2, phi 3. Okay, so this is just very general discussion, but this, in summary, in summary, so when one does conformal field theory, so you should really think of conformal field theory as a recipe. It's a recipe to define and to compute partition functions. To define and compute partition functions or correlation functions, but as I said, these are intimately related. And in particular, again, what is important here is that you can forget path integral calculations. In fact, you can just forget the target space. The target space almost never shows up. Actually, never shows up. And so, and this is what is usually disturbing the first time you look at, first time you open a textbook about conformal field theory, is that you expect to see an action, you expect people to compute path integrals, and I don't know, perhaps to use Feynman diagrams or whatever, use the standard techniques of perturbative field theory. But this is not at all what one actually does. Instead, what one does is that one defines a set of rules, consistency rules, that are inspired, that are not God-given. They are just, coming from motivations from a concrete microscopic model, such as, for instance, classical statistical models at the critical point. Think, for instance, at the critical Ising model. So we look at consistency rules from these microscopic models, and one works with that. Okay, so that's the general discussion, general motivation, and now let's look at the first of these consistency rules. Any questions about this, or? Okay, so the first general object that is always there in our conformal field theory is the stress tensor. So what is the stress tensor? So the stress tensor is a local operator. Local is the key word. So it's a local operator whose expectation value, or one-point function, tells us how the partition function changes if we change the geometry a little bit. So if we, and the little changes of the geometry are encoded into small variations of the metric. So it determines the variation of the partition function under small change of the geometry, namely small change of the metric. Okay, so I will not do much about conformal field. I mean, about field theory on in curved space or with in arbitrary coordinate systems. But just to state what is the stress tensor we need it. So I'm going to write one formula in general coordinates. So to be more precise, what we have in mind is that minus the log of the ratio of the partition functions, so of our surface here, let's say our surface like this, in a metric g plus delta g, divided by, so same surface but now with a metric g. So we have changed the metric a little bit, so it changes the geometry a little bit. We look at minus the log of this ratio because this is the variation of the free energy. So this, we want it to be local, which means that we should be able to write it as the variation of the metric at point x integrated over x with the volume volume element here, times something local, and this something local we call it the the expectation value of the stress tensor, evaluated in the surface with the metric g. And then there's a convention for the normalization, which is to include a factor 1/4 pi here. And this is integrated over the whole surface. Okay, so the key point here is that this, and this is, you know, it's not something we derive from anywhere. We just postulate that in the theory there is such an object, the stress tensor, and this stress tensor, the motivation for this is that we are always thinking of local physics. So there should be, we are thinking of partition functions that have been obtained after integrating out degrees of freedom with a local action. And the locality of the action is encoded in this assumption here, in the fact that we can express everything in terms of a local operator. So this is, you can take this as a definition of the stress tensor. And the key point is that we see that it relates the variation of the partition function or the free energy to a correlation function. To a correlation function of a local operator. So we already see that, you know, as we start exploring consequences of locality, we already see that partition functions and correlation functions cannot be completely independent. There are some rules that they need to satisfy. Okay, so this is quite abstract, so let's immediately have a look at how this works for the Gaussian free field. So for the Gaussian free field, so for the GFF, so the partition function would be, okay, so this time we can, for the GFF, we know that we can write it as a path integral. So that's fine. So for the GFF, we would have this, would be in general coordinates, the action of the GFF is like this. This is square root of, by the way, G is determinant of G, right? This notation here, square root of G, this means determinant of G, d2x. And so then if we can vary this. So we can vary the z, or more precisely log z, minus log z. So we look at the variation of minus log z as we vary the metric, and you can check that this is 1/4 pi. This is of the form that I advertised here. TAB delta GAB square root G d2x with T with TAB equal to at point X equal to 1/2 of 1/2 GCD minus GAC GBD times DCH DH. Okay, this is a calculation that you can do. It follows from looking at the variation of, you need to vary all the different pieces inside that action independently. Okay, so it comes from, so the metric itself varies as this. Then the inverse of the metric, which is written with upper indices, that's GAB minus GAC GBD delta GB delta GCD, and the square root of the determinant of G. You can check that this varies as square root determinant of G times 1 plus 1/2 GCD G delta GCD. Okay, so this is a calculation that you can do. Okay, so this we will need. This is a calculation you can do, and then so these are the components of the stress sensor for the free boson. And now we are going to move to conformal or complex coordinates. Conformal coordinates. So these are coordinates in which the line element can be written as lambda squared dx squared plus dy squared. So right, so locally this is the same as the complex plane with coordinates x, y up to a conformal factor, and then we use complex coordinates here, and so that we can write this as dz bar. Now, if we use these coordinates, then the components of the stress tensor look like that. So tzz is txx minus tyy plus I 2x txy. Tz bar, z bar, this is the complex conjugate of this one, and tzz bar, this is txx plus tyy, so it's the trace of the stress tensor. Now this is completely general. It's just this is just writing things in complex coordinates. Okay, and so now let's just have a look at what these components are for the Gaussian free field. Let's write it here. So for the Gaussian free field, one finds that tzz, okay, tzz like this. This is proportional. Okay, there's just a multiplicative factor that I'm omitting for now. We'll be more careful about this later. But this is d z bar h squared, and to make sense of this operator, we need to regularize it. So we need to use point splitting regularization. T z bar, this is proportional to dz h squared. And finally, t z bar, this is 0. So that's what happens for the free boson. And now the fact that the most important thing here is that TZZ bar, so the trace of the stress tensor, this is 0. So why is it 0? So it's 0 because if you think of what is the stress, is the trace of the stress tensor, so the trace of the stress tensor is what couples to the diagonal part of the change of the metric, and that corresponds to scaling transformations. So the fact that the stress tensor is 0, this is a very general fact. It's not true only for the free boson, it's true for any CFT. This follows from the fact that that the theory is scale invariant. So in a scale invariant theory, the trace of the stress tensor vanishes, at least on surfaces without curvature. But I don't want to enter discussion of curvature. So the trace of the stress tensor vanishes. That's the first important part. And then the other important fact is that we see that the two remaining components, one of them is holomorphic and the other one is anti-holomorphic. And so why is that true in general? In fact, this can be traced back to the Ward identity that is associated with conservation of with translation invariance. Yeah, so I mean, okay, so you can use Noether. Okay, I'm assuming that you have had a first course in field theory, and so that these things you know. But so if you apply Noether's theorem for translation invariance, you know, you will find that the divergence of the stress tensor is 0. And so this gives, when you write this in complex coordinates, here this means that dz tz bar zz is 0, and dz bar tz bar z bar is 0. Namely, this component is anti-holomorphic and this one is holomorphic. So this is what's happening here, and it's completely general. Okay, and now the last important thing, and then we can take the break, is that now we are talking about conformal field theory, so we need to know how the stress tensor behaves under conformal maps. So in general, one defines. Okay, so this is just a convention. But it's the same convention in all conformal field theory textbooks. So the general convention is to define Tz as 1/4 of Tz bar z bar. The notation makes sense because we see that this component is holomorphic, and T bar of z bar as 1/4 of Tz z. And then also Tz z bar, this is 0, as I said. That's the trace of the stress tensor. And then these two components transform as follows under a conformal map. So T of z is dw d over dz squared T of w plus c over 12 times the Schwarzian derivative w of z. And there's a same relation for same transformation law same transformation law for T bar of Z bar, possibly with a number, possibly with a different numbers, possibly with a number that is not C but C bar. Okay, so that's why is that? Well, because it's the most natural guess that you can come up with, knowing how things behave for the free boson. You can argue, but we won't do that, that this is the only thing that makes sense to consider as a this term here is the only one that makes sense. But anyway, so this is the general rule, and this number C here that shows up, this is called the central charge, and it is a key physical quantity in the theory. So now we take the break. After the break, we'll explore at length consequences of this central charge in concrete examples, and we'll derive a few universal results about systems that are all coming from this formula here. Any questions? Yes. I cannot hear you. Why two? I gave only one. Which way? Here? That's not the definition. I mean, that's not the definition. That's just that's the law under which that's the transformation law of this object, but it's not the definition of the object. I mean, if you want, I mean, you know, TW is not more well defined than T of Z. It's yeah. The definition is this. The definition is this. Yes. That part is easy. That part is easy. It's just that's just dimensional analysis, right? It's just because this is the stress tensor. It's you see from the action here. This whole thing should be dimensionless. Therefore, this must be 1 over distance squared. And so the only thing that makes sense here is this. The only thing that would scale as 1 over distance squared is compatible with scaling as 1 over distance squared is this to the 2. 2 is because it's an object of dimension 2, and then it has to be holomorphic because we said this component is holomorphic. Okay, let's take the break. Showing up when one considers partition functions. So let's look at what it says about partition functions. So the first and perhaps most important example I want to consider is the central charge. So the appearance of the central charge when one looks at long cylinders. So a partition function of long cylinders. I mean, you know, I promised applications long cylinders at this point might not sound like a super exciting application, but you'll see later why it's important. So we consider this setup. So we look at a cylinder like this of circumference L and of length capital L. Let's use coordinates x and y. And okay, so this is a surface. We can imagine that there's a conformal field theory defined on it, and this conformal field theory allows us to compute the partition function of this thing. I mean, on the left and on the right, we can, for instance, choose some. We can decide that there's some boundary condition here and there, or just that the system is infinite, and we look at the contribution to the partition function of some piece of the cylinder. And in any case, the claim is that this will pick up a contribution, multiplicative contribution that will go as exponential times the length of this cylinder. So that's so the free energy is extensive with the length, but then it depends on so it depends on the ratio of the length divided by the circumference. This has to be in a scale invariant theory, because in scale invariant theory we can have something that depends only on this ratio. And then there's a number here which happens to be pi times the central charge divided by 6. And when I write that, I'm assuming that I'm working in a theory where the chiral central charge and the anti-chiral one are the same, which is the most, by far the most common situation. Okay, so this is the claim, and this is a very, very, very important result. Okay, so where does it follow? So where does it come from? Play with the definitions to derive this result. So let me just sketch the derivation. It follows from a conformal map from the cylinder to the plane. Do you remember which map this was? So map Z goes to W. This is the plane. What map was that? Yes, it's the exponential. Thank you. And here, okay, so we need, because our cylinder has circumference L, the right normalization is 2 pi over L times C. Okay. Okay, so we have a conformal map. So what can we do with this conformal map? I erased the important formula. So remember, the important formula was that T of Z, that was D of dW over dZ squared times T of W plus C over 12 times the Schwarzian. So now W lives in the plane, and something I didn't say, but I should have said, sorry, is that in the plane, the expectation value of the stress tensor is always 0. This is because if you stretch the plane, for instance, you decide to multiply all distances along in the horizontal direction by 2, but not in the y direction, so that it's not a global scale transformation. It's something that really stretches space. But this doesn't do anything in the theory because it just maps the plane to the plane. So in order for this to work, the expectation value of the stress tensor needs to be 0. So in the plane, expectation value of the stress tensor is always 0. Which means that now if we compute the expectation value of the stress tensor on the cylinder, we pick, okay, so this is 0 because this is in the plane, and we see that this is simply equal to C over 12 times this Schwarzschild. Okay, so this Schwarzschild you can compute. You just apply the formula, and you will find that this is minus 1/2 2 pi over L squared. Sorry, times C over 12 times C over 12. And so this is minus pi squared C over 6L. Good. So this you can compute. And now, okay. So now we have to we want to use this formula over there. Yes. So it's not 0 on the cylinder, it's 0 on the plane. Well, I tried to sketch an argument. If you're not happy with the argument, let's discuss this later, maybe. Okay, so you can look at the formula for the, if you're not happy with the argument I just gave, which is that if you stretch the plane, it's still the plane, and therefore this was the argument. Ah, you didn't hear it, sorry, okay, sorry. You're right, probably L squared. Yeah, probably, must have a typo.
The metric will be like 1, 1, 1, so there will be no variation.
Let's discuss this later, because I don't want to spend the next 20 minutes on why the stress tensor vanishes in the plane. But it's important, but there are other important things to discuss. So okay, and then we need to use this formula over there. In order, and so to do this, so what we can do is we can look, for instance, so there's several things that one can do, but one thing that one can do is to look at the variation of the partition function for this cylinder here, for a circumference little l plus delta L divided by z of L. Okay, so is it clear what this is? So I take this long cylinder and I change the circumference a little bit, and I want to see how the partition function changes. I'm going to apply this formula, so I take minus the log of this, and I look at the variation of the free energy. So now I want to get this from a change of the geometry or a change of the metric. So what change of the metric can I consider? Well, the easiest thing to do is to change the line element in this way. So this is the line element before we have done anything, and then we change it to, this is the original line element, and then we change it to L plus delta L over L squared dy squared. Right, so this stretches the length a little bit in the y direction, in the vertical direction. Okay, so if we do this, if we change the metric in this way, then we are done. Then it stretches the circumference of the cylinder a little bit. Okay, so we consider this change of metric. We apply the formula that's over there, and we find that when we write things in these complex coordinates, This happens to be given by minus t bar times 2 delta L over L dx d2x. Okay, so this you can do. You can check that this is correct, and then this is expectation value of this thing, and the expectation value we know from here, from this formula, so that we know that it's minus pi squared c over 6 L squared, and so the result is pi c over 6 L squared delta L. And now this is the variation of the partition function with respect to delta L. So you can integrate it. You can integrate it, and you will arrive at that. Okay. Now, before I tell you why this formula is important for practical applications, let me just quickly flash a few other cases where you can do the same kind of trick, play with the same kind of tricks, and get similar results. So, yes. Sorry? Up to multiplicative factors of order 1. Of order 1 when L goes to infinity. So if you change the boundary condition, if you put some specific boundary conditions, then it will include insert a factor of order 1 that might depend on the boundary condition and so on. But it won't change the scaling with L. Yes. Yes, but I think I'm gonna say that later. Yeah. But in the pure CFT, that's what you get. Yes. Okay, so this is what we just derive. Now another geometry that I mean you might think is completely crazy, but it's actually also important for applications is to consider conical, so-called conical singularities. So that's what happens when you have when you consider a surface with a cone. So a cone is, I mean, if you picture the cone from above, if you look at it from above, it looks like this. So it's a slice. It's like a slice of the full plane where you identify the points here with the points here with some angle alpha here. One way to get that, for instance, if you're thinking of a critical statistical model on a lattice, for instance, would be to consider, I don't know, an Ising model, for instance, on a square lattice, and you would, for instance, cut a quarter of the plane and identify these points to these points. Okay, and that would create a cone like this. The cone would have angle 3 pi over 2. Now, it's also sometimes actually interesting to consider geometries like this, where the angle is larger than 2 pi. For instance, this would be a geometry where the angle would be 3 times 2 pi, would correspond to 3 sheets that are glued together like this. And this is the kind of Riemann surface that we already saw in the first lecture. Okay, so this is also a conical singularity, just with an angle larger than 2 pi. Okay. Okay, so how do you compute the contribution to the partition function that's coming from this such a singularity? Well, you can again find a conformal map. It's always the same trick. You find a conformal map to the plane. In this case, that's just a conformal map, z to the 2 pi over alpha. Expectation value of the stress tensor in the plane is 0, as we said. And then you find that the expectation value of the stress tensor on this cone geometry is given by this. You play the same kind of trick, you find the right change of metric, you integrate, and you find that in the end that the partition function will pick up a singular term that will look like this. It will scale as the size of your surface. And here, okay, so to make sense of this, you need a UV cutoff this time. So here you see, here this on this geometry there was a natural dimensionless quantity, which was the ratio between the length and the circumference. In a geometry like this, there is nothing that is scale free, that is dimensionless. So what happens is that you pick up a ratio between the infrared cutoff, which is the total size of the system, by the UV cutoff, which is here, for instance, lattice spacing. If you have a small, if this is coming from a lattice, an underlying lattice model, and then you have a lattice spacing A naught, what you will pick is a contribution to the partition function that will go as L over A naught to some exponent, and this exponent you can compute from what I said before, will go as this. Okay, so another case that is important for applications is infinite strips. So that's now a case with a boundary. It's very similar to the cylinder, but now with boundaries on left and right. And you can show, with using the same tricks, that the partition function would go as this. Would be, ooh, I'm sorry, I messed it up. It should be capital L over little l. Yeah, this is the other way around. Sorry about this. So it's essentially the same formula as here, just this factor 1 over 6 that turns into a 1 over 24 for some reason, because now it's an now you have open boundary conditions. Then you can also look at corners at the boundary. Corners at the boundary are similar to conical singularities. You find the same kind of result, again with a slightly different coefficient. It used to be C over 12, now it's C over 24, and there used to be 2 pi's here, now it's pi. Anyway, but it's the same kind of result. Okay, so let me just summarize these 4 cases here on that slide. And now let's discuss a little bit why this is interesting. Any questions at this point? Yes. Sorry? Yes. Yeah, I probably messed it up. This should be 1, yeah, 1 over. Should be this, yeah. Yeah. Or no, wait, no. It is 1 over L squared, but I forgot, sorry, I forgot factor L, capital L. Okay, yeah. Okay, so let's discuss some applications of this. All right, so the first application that we can discuss quickly is the so-called critical Casimir effect. So what's the Casimir effect? Anyone knows what the Casimir effect is? Yes, so it's if you have 2 conducting plates and you have you know, so the electromagnetic field that is quantized, it's fluctuating, and because of the fluctuations, the plates either attract each other or repel each other, depending on what exactly you choose as boundary conditions. Anyway, so here, you know, you can also consider this in statistical physics. So, for instance, there are experiments, perhaps not in 2 dimensions, but maybe in 3 dimensions. But in any case, this is something that there's a community of people that is investigating this very actively. So it's called the critical Casimir effect. So what you can imagine is that you have, for instance, a liquid between two plates, and two liquids, so a binary mixture of two liquids that are not miscible, and you look at so you bring them close to the miscible transition, so that you know, so you can think of these two black dots and white dots here as two different kinds of liquids. There's some surface tension, but if the conditions like a temperature are sufficiently high, then they will be willing to mix. And at some point there's a transition, and then they are completely mixed. And this transition very often turns out to be in the Ising universality class. So if we consider a two-dimensional model for this, then we can imagine that we have two plates and a critical Ising model in the middle, and so which again this would be a liquid mixture at a critical point, and then what we would see is that there would be a force applied between this liquid here would apply a force between the two plates. And what's the force? Well, the force you can derive from the free energy that we just got. For the infinite strip. Okay, so for this critical Casimir energy, we would find that there's a force that would be given by the derivative with respect to the sorry, I shouldn't have called this capital L. This used to be, so this was large capital L and little l. So the force would be the derivative of the minus the derivative of the free energy with respect to little l, right? And with what we have, with what we wrote earlier, we know that this should be pi c over 24 times capital L over little l. And so this way you can compute the force. And the force is universal. It depends only on the central charge. And so that's a nice, powerful result. Okay. Another nice application of these formulas is perhaps might be a little bit unexpected, but historically it was a very important example. It's about hearing the shape of a drum. So do you know? Okay. So have you heard this sentence before? Yes. So you know what the problem is about? How would you formulate the problem? Yes. Yes. So okay. So this is the title of a famous paper by Katz, a mathematician. So the problem is the following. So if someone in some other room is playing on a drum. So what's a drum? A drum is a vibrating membrane that is attached to some frame. So let's say we have some polygonal frame, which is a piece of the plane. So the membrane is fixed on these boundaries, and then if you hit it, so you hit it with a stick or something, then it will generate vibrations, right? So the membrane will vibrate, so we don't see the shape of the membrane. We don't see the shape of the frame, but what we hear is the spectrum of this thing. So we hear the spectrum. So the information we have access to is the spectrum of the Laplacian. The spectrum of the Laplacian on this domain with Dirichlet boundary conditions. Now, so how is this connected to what we have been discussing? Well, because if we look at the partition function of the free boson Gaussian free field, then it is precisely uh, so if we look at the partition function of the Gaussian free field, then just because this is a Gaussian, you have to compute a Gaussian integral, you will find that this is the determinant of minus the Laplacian to the minus 1/2. And this is the Laplacian on the domain U. If this is some domain U, this is the Laplacian on domain U with Dirichlet-Boundary conditions. So the partition function is sensitive to the spectrum of the Laplacian. Actually, it's the product of eigenvalues of the Laplacian. You need to properly regulate this because otherwise it's just infinity. But one way to properly regulate it is to put a cutoff, some cutoff A naught. For instance, you put it on a lattice and you look at the spectrum on a lattice or something like that. And you take the limit of A naught going to 0. And now the question that was asked by Katz about hearing the shape of a drum is, so from the spectrum, from the knowledge of the spectrum, can you infer the shape of the drum? In other words, can you have two polygonal domains, I don't know, for instance, this and this. Can two polygonal domains have the same spectrum? Polygonal domains have the same spectrum. The Laplacian on these two polygonal domains. Okay, so that's a legitimate mathematical question, well posed. But as physicists, what we see is that if they have the same spectrum, then they should have the same partition function. So, so if this, if this thing has angles alpha 1, alpha 2, alpha 3, and so on, this one has alpha angles beta 1, beta 2, beta 3, and so on. Well, the partition function, since if the spectrum is the same, then the two partition functions should be the same. So we should have this equal this. But we saw that these corner singularities have an effect on the partition function. Namely, they induce a term that is going as system size L. So this would be system size. So a ratio between the infrared cutoff and the UV cutoff going as, and forgot the formula, was this case over there, going as this thing, right? This one. And so we see that if they're going to have the same partition function, then they should have alpha I over this identity should be satisfied. So, it doesn't completely answer the question of Katz, but it puts a strong constraint on the shapes that could possibly have the same spectrum. If these two numbers are not the same for your two polygonal domains, then for sure they cannot have the same spectrum. Yes? So I think this I don't know, actually. This I don't know. Perhaps you could cook up examples where these would be the same. But I think all the examples, so the final answer to, I think there was a final answer provided to this question, I don't remember when, maybe the 80s or 90s or so. But I think all the examples that I've seen, so the answer is negative. So you can have two different polygonal domains that have the same spectrum. But I think all the examples I've seen, they have exactly the same sets of angles. They're just playing with the lengths. So I'm not sure you can have different angles, actually. I don't know. It's not something that is told by this formula. Um, okay, so now how much time you have? 5 minutes maybe, or 5? Okay, so one one other example that is interesting is the heat capacity of a quantum one-dimensional quantum critical system. Heat capacity of 1D quantum critical system. I'm running out of chalk, sorry. So yeah, okay. So what we have in mind now is a quantum system. Think of a spin chain, for instance, or a spin chain or a one-dimensional quantum gas that is critical. That means it has the excitations are gapless, so that it doesn't cost energy to excite the system. And in such a system, say of length L, the excitations, this would be described by a conformal field theory, or if you prefer, by a massless theory. So in such a system, the excitations all move at the same velocity. Because if this is not the case, then it means the theory must have a mass. So they all move at the same velocity, which is like the speed of light for this medium, and they move either to the right or to the left with velocity plus v or minus v. Okay, and we consider this system at temperature T, at some low temperature T. And then the claim is that the heat capacity per unit length, which is defined as the derivative of the internal energy with respect to the temperature, that's the internal energy, with respect to temperature. This is pi over 3 times c, so again the central charge shows up, times t divided by h bar times the velocity. So where does this come from? And this is again completely universal result. So if you know in principle how to measure the heat capacity of your system, you are measuring the central charge. Okay, so let me just briefly sketch the calculation that leads to this. So the calculation can be done as follows. So we have a Hamiltonian for this system, and then the internal energy is the expectation value of the Hamiltonian. That's the mean energy taken at temperature T. This we can get by taking the log of the partition function. The partition function is the trace of exponential minus h over t. Right, so this is our Hamiltonian. Let's put a hot on it. Like this. And then I want to differentiate this with respect to t, and I need to multiply by squared in order to make things work. All right. But now this is the partition function of our quantum system at temperature T. And so we might also, you know, if this is described by a conformal field theory, then we would say that this is the partition function of a cylinder like this of length L, because that our system is of length L, and this would be the length in the imaginary time direction through, quantum classical correspondence. And this length here, if you think about it, has to be h bar times v divided by temperature. So the lower the temperature, the longer this length, and then there's some factor to make it dimensionally homogeneous to a length. That's h bar times v. Okay, but we know what this is. We know that what this is because we have computed the partition function of long cylinders, and so this is log of exponential pi c over 6 times L over h bar v over t, and so this gives this result. Okay, now yet another application to one-dimensional quantum critical systems is the entanglement entropy. So I will not have time to do the entanglement entropy really properly. I will just very, very briefly sketch why this is connected to what we have said. Entanglement entropy also of a 1D quantum critical point. 1D quantum critical point. So the setup is the same as here. We have a one-dimensional quantum critical system of length L. We take a bipartition A, B. We trace out B to compute the reduced density matrix. So we take our ground state. This is the ground state. We trace out B to get the reduced density matrix, and then we compute. So we compute the Renyi entropy. Let's call it Sn. That's the log of trace rho A to the n. Okay, now, so it turns out this is exactly, if you think of what this is, again, in two-dimensional Euclidean space-time, it's precisely the kind of surface that I've been drawing earlier, something like this. And so what you end up getting is a conical singularity here. And so you find that this thing, because of the formula I wrote earlier, this is 1 over 1 minus n log of system size L to the C over 12 n minus 1 over n. And from there, you get the usual result that the von Neumann entropy, which is the limit when n goes to 1 of this thing, this is C over 6 log L. Famous formula. Also comes for free. Then other applications. So if you okay, so if you these things are also useful when you think about two-dimensional systems. Maybe I should stop. No, I could just very quickly flash the. Okay, so another thing is the thermal Hall effect. So the thermal Hall effect, the setup is the following. So you have a two-dimensional Hall bar. So that's a gas of electrons in 2 dimensions, pierced by a very strong magnetic field here. So the electrons, okay, there's some very important, interesting physics going on in the bulk, but I don't have time to explain this. But what you have typically is that at the edge, this is infinite in this direction, at the edge of the samples you have your electrons here have gapless excitations that can move to the right on this side, and gapless excitations that can move to the left on that side. I mean, this is quantum Hall physics in 30 seconds. And then, because these gapless edge modes, turn out to be described by a conformal field theory, and using again the same formula, exactly this formula for the cylinder, you can show that the energy current JE, so that's the current of energy flowing through the system, which is corresponds to the energy carried by these modes minus the energy carried by these modes. This happens to be, so sorry, I forgot something very important. The two modes, because they are spatially separated, they can be at different temperatures. So you can have a temperature tau T left for the temperature for these modes and T right for the temperature for these modes. So there's a gradient of temperature through the system. Gradient of temperature, and then the heat current, again through this formula over there, turns out to be given by pi c T right squared minus T left squared. Again, this you get for free from here. And then finally, yet another one, and then I'm done. Is the following. So this is an out of equilibrium setup, also for a one-dimensional quantum system. The setup is the following. So you imagine that you have a 1D quantum critical system, and for some reason you want to prepare it at some temperature. T, let me call this T, this one T left and this one T right. Okay, so I prepare the system. Initially, these two systems do not talk to each other. I prepare the left one at temperature T right and the right one at temperature T left. And why am I doing this? Because then I glue the systems together, I let them evolve, and then you see what happens is that some particles here are going to go to the right. So it's like this part of the system is going to expand to the right, and this part here is going to expand to the left. And so as a result, if I look at the system in this part, then I see that the right moving excitations, those are at temperature they have been prepared at a temperature T right, and the left moving ones have been prepared at temperature T left. And so then I can ask what is the energy current in the middle of the system. I can ask what's the energy current, and then again everything follows from looking at this partition function over there, and you find that this is pi c over 12 T right squared minus T left squared, and that's it. So in fact, it's the same formula as this one, it's just the physical setup interpretation is different, but technically it's exactly the same thing. So conclusion: central charge is important. Central charge is important for applications, and in particular, every time someone shows up and shows you a universal result that involves only the central charge, well, usually you can trace it back to this formula that the expectation value of T in the right geometry. Then, of course, the whole problem is to find the correct interpretation and find the correct geometry. But in the end, it's all coming from the fact that the expectation value of T is C over 12 times the Schwarzian of this map, where this map maps you to a simpler geometry, usually the plane or the upper half plane. And that's it. Thank you.